Any sufficiently advanced technology is indistinguishable from magic, but what if that magic is already hiding in the universe, just waiting for us to uncover its secrets? Today's topic is Clarketech, a term we use on this channel to refer to technologies that operate outside the bounds of known physics. We've got a lot of ground to cover, so you might want to grab a drink, a snack, or even a slice of pie to enjoy while we dive in. The concept of Clarketech comes from Arthur C. Clarke's 3 laws, particularly the third. These laws are: 1. When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. 2. The only way of discovering the limits of the possible is to venture a little way past them into the impossible. 3. Any sufficiently advanced technology is indistinguishable from magic. The third law is the most famous, but all 3 emphasize why it's wise to avoid dismissing possibilities outright. However, this idea shouldn't be stretched too far. Constantly claiming anything is possible risks intellectual laziness. Science rarely overthrows its fundamental principles, but instead builds on them, refining its understanding and discovering exceptions that often reinforce the broader rules. On this channel, we usually explore futures based on known science, illustrating how many impressive achievements could be possible without needing technologies that seem magical by today's standards. Still, we recognize that our current understanding of the universe is incomplete. As science progresses, answers to unresolved questions will undoubtedly lead to even more questions and possibly revolutionary discoveries, akin to those brought by quantum mechanics or relativity. Defining Clarketech. Clarketech is not simply about saying anything is possible, it's about asking what might be plausible if specific aspects of our understanding of the universe turned out to be different. It includes not just speculative ideas, but also common staples of science fiction like Ascension machines, teleportation, or faster-than-light travel. Many examples of Clarketech already have well-known names, and while we've covered some in detail in previous episodes, today's focus is on providing an overview. We'll discuss not just the technologies themselves, but their potential implications for civilization. Implications for civilizations are often overlooked when sci-fi presents examples of Clarketech, particularly in films and comic books, which tend to focus on the immediate utility of these technologies rather than their broader impacts. Today, we'll be contemplating those wider implications, how such amazing technologies could influence civilizations, including alien ones, and whether they might play a role in us encountering them. We'll delve more into that shortly. This is one of our Compendium episodes, where we touch on a wide range of topics briefly. We've got about 30 to cover today, so even a quick look at each of them will take some time. Hence why a drink and a snack might be a good idea, and while you're at it, don't forget to hit the like and subscribe buttons. You can also help support the show by becoming a member on YouTube or patron on Patreon. As usual for our Compendium episodes, feel free to skip around to whatever interests you, or watch them in order. Here are today's topics: Ascension machines and apotheosis, anti-gravity, Attotech, dark matter manipulation, Disintegration Devices, Dyson Spheres, Entropy Manipulation, Fast-and-Light Travel, FTL, Femtotech, Field Nullifiers and Amplifiers, Hammer Space, Kugelblitz Black Holes, Magmatter, Mass Manipulation, Matter-to-Energy Conversion, Negative Matter and Mass, Neutronium, Parallel Universes and Alternate Realities, Perpetual Motion Machines, Photogravitics and Photoneutrino Devices, Probability Manipulation, Reactionless Drives, Slow Time Fields, Subverse Creation, Technological Suppression Zones, Teleportation and Gateways, Tachyon Tech, Time Manipulation, Utility Fog and Smart Matter, Wormholes, and Zero-Point Energy. As we'll see, some of these are not really Clarketech at all, even though they seem like something only the most advanced civilizations could achieve, while others are common in science fiction but likely utterly impossible. We often see these in the hands of fictional alien visitors. But before we jump into discussing these cool Clarketechs, let's consider what it would mean if aliens did exist and had these technologies. Fermi Paradox and Implications. This episode is not focused on the Fermi Paradox, the big question of why we don't observe ancient alien civilizations in a universe so vast and old, but instead considers how plausible a technology is by examining its potential impact on the Fermi Paradox. For example, ultra-cheap energy production and practical interstellar space travel would make it easy for a civilization to expand throughout its galaxy and even beyond. Since life that climbs up Darwin's ladder to the top of its planet's multi-billion-year tall pyramid of skulls does so by being generally inclined to grow in numbers and expand into new niches, we assume most alien civilizations would be inclined to colonize empty spaces when it becomes feasible. Solutions to the Fermi Paradox, therefore, often need to explain why advanced civilizations either would not want to expand, would destroy themselves before they could expand, or would be unable to expand. Alternative explanations include why they might never develop complex technology or life in the first place, or why they might visit us but hide their presence, or even openly visit while we refuse to acknowledge it. We have episodes exploring all these possibilities, including a Fermi Paradox compendium of terms and solutions that walks through them in light detail, while other episodes deep dive specific solutions. Today, however, we are focusing on loud aliens. These are civilizations that leave an unmistakable and enduring presence, big, visible, and long-lasting. Loud aliens engage in mega-engineering feats like building Dyson swarms, which block most or all of a star's light to harness its energy, and doing this across many stars as they slowly expand outward. Such activities would create glaringly obvious signs of their existence. This tendency to make enormous and detectable changes is what we call the Dyson dilemma of the Fermi Paradox, which explores why we don't observe such civilizations. Interestingly, many advanced technologies only exacerbate this Dyson dilemma, as their absence raises more questions about why no loud aliens seem to exist. FTL travel, for instance, makes galactic colonization significantly easier and allows intelligent life to be much rarer while still potentially reaching us. A civilization could originate tens of billions of light years away, and within less than a billion years of discovering FTL, they could still manage to colonize our galaxy by now. Time travel Clarketech means they need not even exist yet, and could still colonize our galaxy right now from a distant future, where they had evolved. As we go through Clarketech options today, we can ponder their realism at least partially through the lens of wondering what such technologies would permit, and if its existence by order aliens might still permit us to even exist, rather than being their 9 trillionth colony planet. Ascension machines and apotheosis. A lot of Clarketech and science fiction and futurist speculation involves options for ascending to higher planes of existence. The aliens and their ancient empire are gone because they ascended. This might range from an apotheosis device that transforms someone into an outright god, to breaking out of the simulation of their reality, or being elevated as an uploaded transhuman or posthuman mind on a planet-sized computer with an IQ of 1 billion. More modern fiction tends to focus on the latter, because as we explored in our Post-Human Pathways episode last year, there are many routes besides simply pursuing mega-intelligence. We also can't rule out the more classic apotheosis examples, where individuals gain access to vast psychic or reality-altering abilities. Indeed, if we do live in a simulation, or some other type of subverse, it would be reasonable to assume the existence of equivalents to cheat codes, like those exploited by Neo in the Matrix film franchise, which would effectively function as magic or psychic powers. That said, our clearest 2 pathways to effective ascension under known science is either to become something godlike in a simulated reality, or to transform yourself into something post-human that operates on a computer substrate millions, billions, or even trillions of times more effectively than neurons. You might have no physical body at all, be a cyborg, be composed of utility fog or smart matter, or have an avatar that could take on any of these forms, or even a regular human body you piloted remotely. When it comes to devices enabling such transformations, fiction often implies some element of self-enlightenment or spiritual growth. However, there are also scenarios where entire civilizations ascend at once. In practice, this would likely be a person-by-person process, with significant portions of the population opting out. This could lead to a slow extinction or bifurcation of a civilization if the remaining population doesn't reproduce enough to offset those ascending. One might wonder, though, what would prevent ascended individuals from reproducing post-ascension. Alternatively, there could be factions within the civilization that refuse to use the technology, discourage its use, or even ban it outright. The exact nature of such a device is impossible to predict, but it might simply be an advanced brain scanner. If so, unless it operates so rapidly, and with such high energy that it vaporizes your brain in the process, which is plausible, you would effectively end up with two versions of yourself: the original person who was scanned, and their copy, now existing on some computer or other substrate. That substrate could be a higher reality or even something carved into space-time itself. The scanned individual presumably remains around, disappointed in their own lack of ascension, as again it was their copy that did that. Anti-gravity. Anti-gravity is quintessential Clarketech, indeed is the only topic-specific episode we ever did as a follow-up to our original Clarketech episode. But between that and our upcoming episode on gravity technologies, we'll be keeping our discussion of anti-gravity fairly brief today. Gravity is a fascinating and peculiar force. Compared to the other fundamental forces, it is astonishingly weak, trillions upon trillions upon trillions of times weaker. Unlike the other forces, which have both attractive and repulsive components, gravity is strictly attractive. It is deeply connected to space-time in ways we still don't fully understand, and appears to behave differently at the quantum level than it does on macroscopic scales. Many theories for dark matter and dark energy also question whether gravity operates differently on extragalactic scales. Given this complexity, numerous theoretical pathways might, if true, open doors to the development of artificial gravity or even repulsive gravity. The implications of such technologies are staggering. If we could turn gravity off, enhance it, or generate a repulsive effect, the possibilities would be limitless. We could envision impossibly tall buildings or structures floating effortlessly above the ground, space stations that hover stationary above the same spot on Earth without needing to orbit, or spacecraft capable of accelerating at extreme g-forces without harming passengers, a concept we explored in the gravitic propulsion episode a couple months back. Personal flight would become a reality, letting us fly around the sky like a bird, but without needing wings. Suspensor platforms might allow us to carry heavy loads without feeling their weight. These technologies could also open the door to advanced space-time manipulation, such as fast-time bubbles or other exotic effects. The potential applications of anti-gravity technology are vast and transformative, and could even allow truly immense civilizations to pack themselves into volumes where normal gravity would cause it to collapse, or hide themselves inside black holes. Attotech. Attotech takes its name from the metric prefix atto, which represents a quintillionth or 10 to the negative 18, making it a billion times smaller than nanotechnology. An attometer is to a nanometer what nanometer is to a meter. At this scale, even a proton, approximately 1700 atometers in diameter, is relatively large, like a mile-wide dot measured in yards. By comparison, the electron size is still uncertain and often modeled as a point particle in many frameworks. The term attotech is far less common than femtotech, which is hardly a common term itself, and which operates at the subatomic scale of protons and neutrons, around 1 femtometer or 10 to the negative 15 meters, equivalent to 1000 attometers. Attotech is typically reserved for speculative discussions about technologies constructed from objects smaller or more fundamental than quarks, such as magnetic monopoles, strings, or other as yet unknown particles. Magmatter, a hypothetical form of matter composed of magnetic monopoles, serves as a prime example of potential attotech applications. The smallest mag atoms are theorized to measure just 0.3 attometers in diameter, making them ideal building blocks for devices at this scale. Beyond attotech, we could hypothesize even smaller scales, such as septotech, yoctotech, rontotech, and kektotech, each stepping down by 3 orders of magnitude. However, these would likely require a deeper layer of physics beyond the quantum scale. I generally group these speculative levels under the term Planck tech, which refers to technologies operating at or below the Planck scale, assuming such a fundamental layer of reality exists. Even attotech might be considered part of this realm, if not for the semi-plausible example of magmatter, which has its own entry today, along with other interesting types of matter. Dark matter manipulation. Our best estimates suggest that there is several times more dark matter in the universe, and in and around our galaxy, than the normal matter we use for construction. Most normal matter is composed of hydrogen and helium, neither of which is particularly useful for building. If we could find a way to use dark matter as a construction material, it would vastly expand our resource supply. The key challenge with dark matter is that while its existence is widely accepted, we still don't know what it actually is. And its existence is still not 100% guaranteed either. What we do know is that it has significant mass, interacts weakly, if at all, with other forces or particles besides gravity, and contains a lot of energy, since mass and energy are equivalent, E = mc squared. We also describe it as cold, meaning the average particles aren't moving faster than the galaxy's escape velocity. This doesn't directly translate to a temperature, as we don't know the size of the individual dark matter particles. However, since the escape velocity of the galaxy is hundreds of kilometers per second, far faster than the ultra-hot particles emitted by a rocket engine, slow might be a better term. Because dark matter interacts so rarely with itself or other matter, it doesn't clump together or form disks like normal matter, which can condense into stars, planets, and other celestial bodies. However, this doesn't rule out the possibility of gravitationally bound spheres of dark matter. In fact, it might be possible to pack dark matter into very high densities, assuming we could find a way to gather it and ensure its particles move slower than the escape velocity of the structure. This property could make it ideal for adding mass and gravity to artificial shell worlds, particularly if spin gravity environments are not preferred. Without more knowledge about dark matter, it's challenging to propose methods for manipulating it. However, we explored several hypothetical variations and technologies, and the technologies they might enable in our Dark Matter Technologies episode, providing a glimpse into the possibilities if we ever unlock its secrets. Disintegration Devices. In science fiction, disintegration beams are a popular weapon because they offer a simple way to remove things or people. From a narrative perspective, they're easy to depict. Point the weapon, cut the camera, remove the target, and later overlay a flashy beam effect. These beams are often portrayed as strangely precise, disintegrating specific objects without harming anything else nearby. This might make sense if the weapon itself were intelligent, which is plausible given the concept of future smart weapons. This raises the big problem: what happens to that disintegrated matter? If the disintegration beam simply transported the matter to another reality or teleported it into, say, a star, then there's little concern, unless of course the disintegrated target could somehow return. However, if disintegration means vaporizing the target at the chemical level, then the matter isn't vanishing, it's being converted into energy. This is where things get dangerous. A human body vaporized at the chemical level essentially becomes a bomb. The energy released is far greater than most conventional explosives of the same mass because explosives like TNT are not particularly energy dense compared to chemical fuels or biological material. TNT's potency comes from the rapidity of its energy release, not the total energy content. An equal mass of coal or oil or even body fat has more energy than TNT. Vaporizing a person with a beam weapon would create a massive explosion, potentially filling the room with superheated steam. While it might lack the destructive shrapnel of a traditional bomb, it would still be catastrophic for anyone nearby. Even worse, science fiction often describes disintegration as atomization, meaning breaking matter down into individual atoms. This requires about 10 times more energy than chemical vaporization. If the weapon goes even further, stripping away all the electrons, or worse, splitting nuclei, then you're entering nuclear territory. This energy release could rival or exceed that of a nuclear explosion, making such weapons wildly impractical for close-range use. There are some practical considerations for disintegration weapons. If disintegration doesn't involve teleportation or transporting matter elsewhere, you're essentially unleashing the destructive power of a bomb every time you use the weapon. For safety, this type of weapon would need to be used at a considerable distance, with the user fully aware of the explosive consequences. A simpler alternative, like a high-powered laser or heat gun, could theoretically achieve the same result, but as we've noted, such approaches are less surgical and far more destructive. Dead is dead, why spend billions of joules of energy for what 1,000 joule bullet might achieve, or just shoot a million bullets instead? An alternative concept might involve a field that suppresses the forces binding matter together, such as atomic bonds. While this raises energy conservation questions, explored in more detail in our discussion of field nullifiers in a few minutes, such a method could theoretically allow matter to unglue without the need for massive energy inputs. However, even this approach wouldn't eliminate the explosive energy release. For example, simply breaking the bonds between atoms in the human body would release energy equivalent to the body's internal temperature. The average human body contains about 10 megajoules of heat energy, roughly equivalent to 5 pounds of TNT. While this wouldn't generate the shock waves or shrapnel of a traditional explosive, it would still create a significant blast, enough to cause serious destruction in the immediate area, something like a dozen hand grenades. Disintegration technology, while a staple of science fiction, comes with significant challenges when viewed through the lens of real-world physics. Whether through energy release or fundamental force manipulation, the consequence of vaporizing a person or object would likely be as destructive as conventional explosives, if not worse. For precise use without collateral damage, the concept requires advanced solutions that may venture into speculative or Clarketech territory, like sticking them in a bubble of space that teleported to another universe. Dyson Sphere. Dyson spheres, along with stellar engineering in general, are often mischaracterized as examples of false Clarketech. While they are frequently portrayed in science fiction as near-impossible structures that only super-advanced civilizations could construct, we actually have a clear technological pathway to building them. In fact, they might be more achievable than many near-future technologies like fusion power or medical nanobots. The misconception likely arises from their sheer scale. This perspective extends to many stellar engineering projects such as star lifting, artificial suns, or M-brains, concepts that are enormous in scope but not necessarily reliant on advanced technologies, though such technologies would undoubtedly help. A Dyson sphere, or more accurately a Dyson swarm, encircles an entire star and by default offers over 1 billion times the surface area of Earth. As many of our regular viewers know, Freeman Dyson originally proposed the Dyson swarm as a cloud of power-collecting satellites orbiting a star. These satellites don't need to be much more advanced than our current ones, and the swarm can grow incrementally, potentially enveloping the star entirely to harvest its energy. Beyond power collectors, the swarm could also host other facilities, including classic rotating space habitats for human habitation. That said, science fiction often depicts Dyson spheres as a giant, hollow, inverted shell resembling a planet. This design, however, ventures firmly into the realm of Clarketech. Even with the necessary technology, I don't see this approach as particularly practical for creating living space, similar to the Alderson disk, though a slightly less ambitious structure like a ring world might work. Ring worlds are massive, spinning rings around a star that use centrifugal force to simulate gravity. These structures require impossibly strong materials like Magmatter, though we've explored some cheats using mundane materials and active support in our ring worlds episode. A series of ring worlds, each at slightly different diameter and tilted around the star, could potentially create a Dyson swarm-like configuration. But why not stick with a simple shell, a classic Dyson sphere? There are several reasons. First, gravity dynamics. A spherical shell generates no gravity inside it. If you were to dig down 100 miles into Earth, the mass above you would cancel out, leaving you with the same gravity as if the planet were 100 miles smaller in radius. Similarly, a Dyson sphere would have zero gravity inside, except for the star at its center. This means everything, air, water, and people, would eventually fall into the star unless artificial gravity generators were used to keep things in place. Then there was structural strength. The shell would need to be impossibly strong to support its own weight. While some active support systems might offer a workaround, the engineering challenges remain daunting. Third, we have perpetual daylight. A Dyson sphere would mean perpetual daylight with no natural day-night cycle. Kudos to the novel Elvin's Star, part of the sci-fantasy Deathgate cycle by Margaret Weiss and Tracy Hickman, for addressing this unique challenge. It's one of the few works I've encountered that seriously explores the impacts of a Dyson sphere on civilizations and ecosystems. Much like with a ring world, the perpetual sunlight issue in a Dyson sphere could be mitigated using mirrors and shades. However, this design would still result in a Dyson sphere significantly larger than Earth's orbit. While we often imagine a Dyson sphere as a shell roughly at Earth's orbital distance from the Sun, achieving Earth-like conditions would require a radius nearly double that, extending well past Mars and approaching the asteroid belt. A significant challenge is the enormous amount of construction material needed. The mass of the asteroid belt falls far short of the required amount, especially since the Dyson Sphere generally assumes a thicker layer of material than the typical space habitats or thin solar collectors. Even if we employ starlifting to extract metals from the sun, this might still be insufficient by an order of magnitude. On the other hand, a civilization with artificial gravity could overcome many of these challenges. Such technology would make harvesting material from stars much more feasible. They might opt to construct the largest sphere possible using a star's available mass while reducing the star's fusion rate to a level sufficient for comfortably illuminating the sphere. The remaining stellar material could then be resorted to extend the star's lifespan, ensuring long-term sustainability for the structure. While they might be able to use gravity tech to forge heavier elements from hydrogen and helium when building around bigger stars. We're looking at hyper-advanced technologies today, and we'll need big brains to tackle those problems. But could big brains be rare out in the cosmos, even on very big aliens? In the Big Alien Theory, our latest Nebula exclusive episode, we dive into the challenges and advantages faced by extraterrestrial species of titanic proportions. From mind-bending technologies to vast possibilities of alien intelligence, Nebula is the place for exclusive explorations. Could bigger brains unlock impossible technologies? How do the physical and resource demands of massive alien species influence their ability to innovate and evolve? Find out now only on Nebula. Sign up today at go.nebula.tv/IsaacArthur using the code IsaacArthur to get 40% off an annual plan, making it $3 a month. On Nebula, you can access all our episodes early and ad-free, along with all our monthly exclusive episodes, like Big Alien Theory, and a host of content from other awesome creators like Up and Atom, Real Engineering, Real Science, The Science Asylum, Simon Clark, and more. Nebula also offers lifetime membership and gift options, so you can share incredible content like the Big Alien Theory with friends and family. Just head over to go.nebula.tv/IsaacArthur and start exploring a universe of exclusive ideas today. And now, back to our show. Entropy Manipulation. One way to extend the lifetimes of stars, or civilizations, might be to reverse entropy in some way. While this seems to blatantly violate the laws of thermodynamics and is often relegated to the realm of Clarketech, it is worth noting that entropy has been increasing since the universe began. This fact always comes with a caveat that the rules governing entropy must have been broken when the universe itself came into existence. There's also nothing inherently impossible about reversing entropy locally by introducing new energy or material into a system. In fact, we do this all the time. It's how power generation works. Entropy only inevitably increases in closed systems, and the observable universe doesn't appear to be a closed system. For example, the Big Bang and the presence of dark energy suggests that energy can enter our reality. The universe isn't an explosion expanding outward from a single point in time like a shockwave. Instead, dark energy drives the expansion of space-time itself, creating new space between objects. The more space that already exists between objects, the more new space forms, creating the illusion that objects are speeding away from one another. This process can even bypass limits like the speed of light, an issue we'll return to shortly. But it is worth remembering that while nothing can cover distance faster than light speed, most of the observable universe is moving away from us faster than light travels. Which is fine for not violating causality, but raises some serious conservation of energy issues. While we don't have any obvious way to violate entropy, the observable universe suggests that energy isn't conserved in the same way it would be in a fully closed system. Dark energy, for instance, is a form of new energy entering our universe, driving expansion. It is also possible this universe's energy, whether from the Big Bang or dark energy, could be leaking from some larger reality, increasing entropy on a grander scale beyond our own. Importantly, we aren't necessarily talking about outright entropy reversal, but rather entropy manipulation. There are quantum phenomena that hint at the possibility of reversing entropic processes, and both dark energy and the Big Bang serve as compelling examples of energy arriving from outside our observable reality. These concepts suggest it might be possible to manipulate entropy on a cosmic scale, potentially steering the universe away from the default heat-death scenario we often imagine. What could we do with entropy reversing technology if we had it? In simple terms, if it were compact and straightforward, you could do something like separate lukewarm bathwater into a hot side and a cold side, which is a lot more useful than it probably sounds like. This assumes no external power source from another universe, just pure entropy reversal. Turn the device off and the two sides would mix back into lukewarm water, generating usable power in the process. However, it is important to avoid thinking of this as a magical time-reversing device. It's not as simple as pointing at a rusted iron plate to make it factory fresh, or at a human to de-age them. Even in seemingly straightforward cases like recharging a decayed radioisotope, entropy reversal isn't about neatly rewinding processes. Entropy is an average of countless individual interactions. For example, in a decayed material, individual atoms have undergone radioactive decay, releasing decay products such as high-energy photons. These photons slammed into other atoms, scattering energy and creating heat. Other particles, like neutrons, decayed into new particles, and neutrinos likely escaped into the void, never to return. Reversing this process is far from a simple flip-a-switch scenario, which is why rising entropy in closed systems is so inevitable. Though in a closed system it should eventually reset, a Poincare recurrence. Much as if you shuffle a deck of cards enough times, it will return to a prior state or card order. This would take untold eons for the deck of cards. For something like the universe, you are talking timelines that can only be expressed using pentation, a math notation even bigger than exponents. See our episode The Library of Babel and Infinite Monkeys for an explanation of that. If we could make entropy reversal work, even in a limited capacity, it would revolutionize civilization. Such technology would untether us from resource dependence, allowing us to endlessly recycle what we have, or perhaps even create new resources from nothing. This would eliminate the need to colonize an entire galaxy, an incredibly challenging feat without fast light travel, to secure the resources needed for growth or long-term survival. This makes entropy manipulation a rare example of technology that breaks the Dyson dilemma of the Fermi Paradox, or at least pushes hard against it. Civilizations with this capability would not need to expand outward to obtain resources, as they could sustain themselves indefinitely. However, they might still face challenges of expansion if population or changing lifestyle pressures necessitated taking up more space, or for other reasons such as the Chronos scenarios, where colonies became significant potential threats. In that case, outward growth might offer no substantial benefit to justify the risks. Faster than light travel, FTL. The distances between star systems are so immense that even a single message sent to and from our nearest neighboring star systems could take a generation to complete its journey. Travel would likely take even longer, making the desire for faster than light, FTL travel, unsurprising. We have an entire series exploring potential FTL options and the significant challenges involved. At its core, FTL represents one of the most elusive forms of Clarketech, arguably more challenging than perpetual motion machines or apotheosis devices. While the latter might feel more fantastical, they at least have some plausible pathways. In contrast, FTL seems outright prohibited by our current understanding of math and physics, though some workarounds may exist. The main hurdle is the relationship between mass and energy. As an object speeds up, its kinetic energy increases, effectively adding mass. This makes it exponentially harder to accelerate further, akin to pushing a wheelbarrow that grows heavier with every mile per hour. Eventually, the energy required to add even a fraction of speed becomes infinite, setting a hard cap at light speed. To exceed that speed, infinitely more energy would be required, making it mathematically impossible. Interestingly, workarounds like warp drives, wormholes, and hyperspaces attempt to bypass these limitations rather than violate mathematical principles. Warp drives, for instance, contract space ahead of a ship, while wormholes offer shorter paths between 2 points in regular space. Hyperspace theory suggests traveling through an alternate universe with different physical properties to shorten the journey. Such mechanisms are mathematically and physically permissible since space-time itself can warp and expand. In fact, most of the observable universe is already receding from us faster than light due to Hubble expansion, where distant objects are carried away by the stretching of space itself rather than moving through space. However, these FTL methods depend on exotic materials or other Clarketech to function, and the energy requirements are staggering. For example, creating a stable wormhole might require hundreds of stellar masses to establish a single gateway between two star systems. Even if the technology were feasible, the sheer energy cost raises valid questions about whether such travel could ever be justified, except in the most extraordinary circumstances. Femtotech. Femtotech refers to technology operating at the femtometer scale, about 1,000,000 times smaller than nanotechnology. This scale corresponds to the size of protons and neutrons, which are typically around a couple of femtometers in diameter. In principle, we can imagine technology existing at any scale defined by the metric prefixes, each step being 1,000 times smaller than the previous. Starting from the macroscopic scale, or human scale, we progress through the millimeter scale technologies, microtech, micrometer scale, nanotech, nanometer scale, picotech, picometer scale, femtotech, femtometer scale, and attotech, attometer scale. Speculative extensions could include even smaller scales such as zeptotech, yaktotech, rontotech, and kektotech, but these delve into realms where our current understanding of physics becomes uncertain. On this show, we loosely define nanotechnology as operating at the subcellular scale, involving structures composed of at least thousands, if not billions of atoms. Picotechnology refers to devices made from only a handful of atoms, while femtotechnology delves into the subatomic scale. Attotechnology, as discussed in its own entry, typically refers to constructs made of magmatter or magnetic monopoles. Beyond that, anything smaller is grouped into Planck tech, referring to hypothetical technologies operating below the quantum scale, assuming such a domain exists. This scale could also be extended in the other direction with terms like kilotech, megatech, gigatech, and beyond. We frequently discuss megastructures, which could theoretically approach the ketometer scale, 10 to 30 meters. For comparison, this is at the opposite extreme of the scale from a kectometer, 10 to negative 30 meters. However, there's a practical issue. The entire observable universe is just under 10 to the 27 meters in diameter, a ranometer. As a result, discussing radatech or ketatech would be somewhat redundant since nothing that large exists within the observable universe. Similarly, with the exception of magmatter-based attotechnology, anything below the femtotech scale is essentially speculative and largely impractical for meaningful discussion, and magmatter often gets rolled into femtotech anyway. Even in this context, we often consider scenarios where space-time itself is being manipulated, such as compacting a machine into a smaller region of space. This could involve folding the space or utilizing a congruent universe. For example, instead of the classic hyperspace concept, where a smaller alternate universe allows for quicker travel before re-entering normal space, this would involve a larger congruent universe. In such a scenario, a room-sized region of the alternate universe might correspond to an atom-sized region in our universe, enabling a macroscopic scale device to operate at an incredibly small scale by interacting through this spatial correspondence. This concept could bridge the gap between large and small scales, allowing for the manipulation of matter at dimensions otherwise unattainable. Lastly, it can refer to constructs made entirely of subatomic particles. This could include matter composed of quarks other than the usual up and down quarks, such as stable atoms formed from positively and negatively charged particles made of strange, charm, top, or bottom quarks. Alternatively, it could involve entirely unknown particles with properties we have yet to discover, or even particles imported from other realities. Field nullifiers and amplifiers. Everything is bound together by forces, the fundamental forces of gravity, electromagnetism, and the weak and strong nuclear forces, along with some theoretical ones like dark energy or emergent ones like the van der Waals force. There are possibilities of higher dimensional forces arising from string theory, exotic matter forces that might interact only with dark matter, or non-local forces that could explain the spooky action at a distance observed in quantum entanglement. If you could nullify or amplify such forces, or control not just their strength but their direction, it would be an invaluable tool, an unparalleled defense, and a formidable weapon. Unsurprisingly, the ability to control forces makes you a force to be reckoned with. You might be able to nullify or dampen nuclear chain reactions, a concept often used by Isaac Asimov and other sci-fi writers to address nuclear weapons defense in various stories. Another example appears in the classic novel Ender's Game, where the ultimate weapon, the Little Doctor, or MD device, used a molecular detachment effect to destabilize the bonds holding matter together. This triggers a chain reaction, causing large objects, like spaceships, to explode. Nearby ships can also be affected, creating a cascading chain of destruction. This weapon is eventually used to destroy an entire planet. Later in the series, we learn that their spaceship engines operate on a similar principle. Like the Bussard ramjet spaceship drive, they collect dust and gas from the interstellar void as they travel, converting into unlimited fuel and propellant. This enables the ships to approach speeds arbitrarily close to the speed of light, gaining the advantage of extreme relativistic time dilation for travel. However, the weapon isn't entirely setting breaking, as a large spaceship traveling at 99.9999% of light speed could devastate a planet on its own, a concept known as a relativistic kill missile. I should also note that if you could work with whatever spooky force involved in quantum entanglement, it might allow some form of FTL communication that did not violate causality. On a more practical level, the ability to nullify gravitational fields, amplify or direct them could enable a range of advanced gravitational technologies. Similarly, altering the probabilities of nuclear interactions or decays could revolutionize energy production, making fusion or fission vastly more efficient. This might lead to compact fusion reactors or even matter-to-energy converters. Furthermore, amplifying or dampening gravity with its intrinsic connection to spacetime could allow for warping of space or time in unexpected and potent ways. Hammer space. In a Clarketech context, hammer space represents a technology that allows objects to exist in extra-dimensional storage spaces, effectively accessing more room than conventional three-dimensional space allows. This idea, originating in cartoons where characters seemingly pull objects from thin air, is often implemented in science fiction as a bag of holding inspired by D&D, or in the TARDIS from Doctor Who, which is famously bigger on the inside. Hammer space implies a manipulation of spatial dimensions beyond those we perceive. A hammer space device could appear as a small object, a backpack, drawer, container, or police box, but internally access vast volumes of space, possibly with separate physical laws. This means hammer space could sidestep typical issues of mass and volume, enabling storage of immense or cumbersome objects without size limitations. The TARDIS is a reminder that we're not necessarily talking just space manipulation, but time as well, space-time being linked. So you might have ones in which time slowed too, unless you can reach into your hammer space pocket and pull out a sandwich you stuck in there last week that's still fresh. Of course, your default bag of hoarding doesn't really imply a very good shuffling and sorting method, which tends to imply you've got some big heap of material in your extra-dimensional space that's rapidly turning into a compost pile. This is where additional technologies of a more mundane variety might come in, like drones inside the hammer space that were sorting things and delivering them on request, and that might include catching your sandwich and putting it into a refrigerator in that hammer space, or it might be that it's a bit like a photo cabinet, where you can flick through with your fingers and expand the section you want at the time, or reach in and grab from. You also need to ask how energy is getting put into that hammer space to run appliances, how fresh air gets in, how heat or carbon dioxide gets out, the general thermodynamics situation inside, and if there's any way to open a door inside an existing one as a back door or to conduct a heist. The applications are endless if you can make something like this work, from obvious things like carrying a warehouse with you or having a gun that never ran out of ammo, to moving planets around or hiding whole civilizations in pocket spaces. While we have no obvious pathway to this sort of technology, there are mathematical pathways to folding space up this way, and if there are near infinite other universes out there that we might be able to reach, an awful lot may be small and stable universes that you might be able to connect via a portal, and then tie that portal to something like a bag or pocket you could carry. Kugelblitz black holes. Stephen Hawking, the renowned physicist, is famously associated with black holes. His most notable contribution to the physics community was his discovery that black holes, traditionally thought to trap everything within their event horizons, actually emit radiation and slowly evaporate over time. This phenomena, now known as Hawking radiation, was both groundbreaking and counterintuitive. Larger black holes radiate more slowly than smaller ones, meaning that the more massive a black hole is, the longer it takes to evaporate. In fact, typical black holes in the universe radiate so slowly that they absorb energy from the omnipresent cosmic microwave background radiation faster than they lose it. they won't start shrinking significantly until long after all stars have died out, and their complete evaporation would take incomprehensible spans of time, on the order of trillions upon trillions of years. However, if we could create much smaller black holes, such as those with the mass of a modest asteroid, say 1 billion tons, we could harness them as an extraordinary power source. Such a gigaton black hole would radiate energy at a rate of 356 megawatts, equivalent to a large modern power plant. Even more impressively, this power output would last for approximately 1.5 trillion years, more than 100 times longer than the current age of the universe. Unlike most power sources, which weaken over time, a small black hole's radiation output would actually increase as it loses mass, becoming more powerful as it nears the end of its lifespan. One that had evaporated to 1,000th that original mass would also be 1,000 squared, or 1,000,000 times more powerful at this point, 356 million megawatts, and would keep climbing slowly in output over its remaining 1,500 years of life. Clearly, we would love to have such things, and the science strongly suggests they can exist, but unless we want to wait several undecillion years, which is 10 to the 66 years, we would either have to make one or find one created by other processes, which we think might have happened and produced lower mass primordial black holes right after the Big Bang. The Kugelblitz method is a proposed way to create artificial black holes. The idea hinges on the fact that gravity is generated by energy, not just mass. Mass is simply one form of energy. If enough energy is concentrated into a small enough region within a short time frame, it should form an event horizon and collapse into a black hole. Once created, the black hole could function as a power source or battery, with the potential to sustain it by feeding it additional material. However, adding mass to such a black hole is more challenging than it might seem, as precisely targeting the event horizon is difficult, amongst other problems. Creating a Kugelblitz black hole would require either colliding ultra-dense rods of material at relativistic speeds, or firing an immense array of lasers to focus energy on a single point. Such an endeavor demands an enormous power supply, ideally harnessing the energy of an entire star. While this may sound like advanced Clarketech, constructing a basic Dyson Sphere to collect stellar energy, often viewed as a foundational megastructure for advanced civilizations, is relatively low-tech by comparison. For more discussion, see our episode on Kugelblitz black holes, but if this technology becomes feasible, it could revolutionize space travel by providing highly efficient spaceship drives and serve as a long-term power source for advanced civilizations. Magmatter. Magmatter, or magnetic monopole-based matter, is a theoretical substance composed of magnetic monopoles instead of traditional atomic nuclei and electrons. I tend to be rather skeptical of magnetic monopoles existing, but there's good theoretical reason to think they might, and if they do, they open the doors to some truly amazing materials that make steel or graphene look like tissue paper, and might let us build megastructures such as ring worlds, Banks orbitals, or even structures greater in scope than a Dyson sphere. In conventional matter, atomic structure is governed by the electromagnetic force, with electrons orbiting protons and neutrons in the nucleus. Magmatter, by contrast, relies on monopoles, hypothetical particles with isolated magnetic charges, just a positive magnetic or negative magnetic pole, to form the foundation of its structure. These monopoles interact through magnetic forces, analogous to how electrical charges form atomic bonds in ordinary matter, but with vastly greater strength and stability due to the inherent energy scale of monopole interactions. One of the most critical features of magmatter is its extreme density and strength. Unlike ordinary matter, which is largely empty space within and between atoms, magmatter's binding forces allow for extraordinarily compact configurations, enabling the creation of materials millions or even billions of times denser than any known substance, including neutronium. Such density would make magmatter incredibly resilient to forces that would obliterate ordinary matter, and offer tensile strength orders of magnitude higher than carbon nanotubes. This opens the door to superhuge megastructures and other ultra-high performance materials, like armor that might shrug off a direct nuclear strike. However, this density also makes magmatter incompatible with ordinary matter on a fundamental level, even assuming monopoles exist. Its interaction with standard atomic matter would likely result in catastrophic energy release, as normal atoms are ripped apart by the intense magnetic fields and energy of the monopoles, meaning it would also make for potent weapons. Still, this can probably be gotten around, so if monopoles do exist, it opens the door to impossibly strong materials and impossibly awesome things made from them. Mass manipulation. Mass is an interesting thing and has properties folks tend not to think about. For one thing, under special and general relativity, it is the quantity that lets us experience time. Massless particles like photons and maybe gravitons do not experience time, whereas things with imaginary mass, like the hypothetical tachyon, experience time backward. Even just its best known properties, resisting forces, carrying inertia, and attracting objects gravitationally, or being attracted by them, are thought to be potentially separate quantities that might be manipulated individually. We might one day be able to adjust mass, either decreasing or increasing it for an object. Inertial mass, passive gravitational mass, and active gravitational mass could each be individually controlled. Imagine an object that could be made lighter in terms of inertial mass, so it accelerates faster than the force exerted on it should allow, or conversely, resist force by increasing its inertial mass. Such manipulation could have applications ranging from spaceship drives to personal defense systems against punches, bullets, or explosions. Raising the active gravitational mass of a brown dwarf or gas giant might cause it to ignite fusion, effectively turning into a star. Conversely, lowering the gravitational mass of a super-Earth could make it habitable by reducing surface gravity, or it might help with resource extraction on mining worlds. Similarly, adjusting passive gravitational mass on a spaceship could allow for faster falls toward a planet by enhancing gravitational pull, while reducing it upon exiting a planet could make departure easier, and vastly boost slingshot maneuvers and the Oberth effect. This concept could also be weaponized, for instance, by creating kinetic impactors that accelerate impossibly fast under enhanced gravity, or bullets whose inertial mass could be modified to hit harder. We discussed additional possibilities for power generation and propulsion in our gravitic propulsion episode a couple months ago. Matter to energy conversion. Your typical chemical fuel provides tens of millions of joules per kilogram or liter, depending on whether you're talking about gasoline, firewood, body fat, or other common fuels. Nuclear fission fuels like uranium, plutonium, and thorium perform far better, about 1 million times more energetic, delivering tens of trillions of joules per kilogram. Fusion surpasses even this, with ideal hydrogen to helium fusion yielding approximately 640 trillion joules per kilogram, about 10 times more efficient than fission. Under Einstein's E = mc squared, however, a single kilogram of mass contains an astounding 90,000 trillion joules, which is 140 times better than ideal fusion and more than 10,000 times better than nuclear fission. This is what makes antimatter so potent, as it annihilates with an equal mass of regular matter, releasing nearly 100% of the mass energy. It's also the source of a quasar's incredible power, where stars or massive gas clouds devoured by black holes convert much of their mass into energy. In the future, artificial micro-black holes could achieve high matter-to-energy conversion rates, potentially yielding 18,000 to 40,000 trillion joules per kilogram. Or we might find ways to cheaply produce and safely store antimatter, yet the ultimate breakthrough would be a device that could literally convert matter into energy, safely and efficiently, at a controlled rate. Imagine a generator, akin to those used at construction sites or during power outages, that requires no traditional fuel, just air or even water. A device like this, running on water as a fuel, could produce 10 kilowatts of power and would take 285 million years to consume a single liter of water. A simple rain collector could replenish it indefinitely. In fact, a single drop of water could power it for approximately 14,000 years, as long as human civilization has existed. It's worth noting that while we might refer to a matter-to-energy converter, in practice the energy it produces would take some specific form. Even with antimatter annihilation, the process involves two particles colliding and converting into other particles, typically a pair of photons, but not always. Photons would be ideal for energy harvesting, as they are relatively straightforward to capture for power generation. However, high-energy photons, like the gamma rays produced by antimatter annihilation, are much harder to manage effectively. A practical matter-to-energy converter might function more like a wood chipper for particles, breaking them down to a million tiny flecks of low-energy photons, similar to the kind of light plants use for photosynthesis so that we use to see. On the other hand, some products of matter-to-energy conversion, like neutrinos, would be far less useful. Neutrinos interact so weakly with matter that they are almost impossible to harness for power or propulsion. However, if directed rather than emitted randomly, neutrinos could make excellent propellants. Since they pass harmlessly through most matter, they wouldn't cause damage even at high intensities, allowing a spacecraft to achieve the extreme power levels needed to move megaton-scale ships without becoming destructive to nearby planets or habitats. This concept of a spaceship drive powered by matter-to-energy conversion has been a staple of science fiction. One of the first and most popular examples is Robert Heinlein's torch drive, which employed this technique. The torch drive has since inspired and lent its name to many fictional spacecraft propulsion systems, embodying the potential of such technology for high-power, efficient space travel, though often as a fusion drive like the Epstein drive from The Expanse. In space, such technology would revolutionize propulsion, enabling near-light-speed spacecraft and powering space habitats for durations far exceeding the lifetimes of stars. Civilizations with this capability might view stars as inefficient energy sources, with much of their potential wasted. Instead, they would likely focus on stockpiling mass in substellar depots, dismantling stars and repurposing their material for more efficient energy production. These civilizations, despite their technological prowess, would still be constrained by finite resources. They would have strong incentives to colonize space, leaving unmistakable footprints on an astronomical scale. Their mastery of stellar engineering and mass stockpiling would make them visible and loud in the context of the Fermi Paradox, as their activities would be both highly motivated and easily detectable. Negative matter and mass. Negative mass is a hypothetical concept in physics where negative matter would possess properties opposite to those of ordinary matter. In conventional physics, mass is always a positive quantity, leading to attractive gravitational forces and behavior consistent with Newton's laws of motion. Negative mass, however, would behave counterintuitively under these laws. If subjected to a force, it would accelerate in the opposite direction of the applied force, moving toward whatever pushed on it. This peculiar behavior has made negative mass a popular subject in speculative physics, particularly for its potential applications in advanced propulsion systems, as discussed in our gravitational spaceship propulsion episode. It's also central to theories about wormhole creation and warp drives. Unlike ordinary mass, which compresses space-time and slows time due to gravity, negative mass would theoretically expand space-time and might even accelerate the passage of time. These properties could enable revolutionary technologies if negative mass were found to exist. To date, no actual examples of negative mass have been observed, and many physicists, myself included, view it as a mathematical construct rather than a physical reality, no more tangible than a negative cookie or a negative gallon of water. Nonetheless, if negative mass did exist, the possibilities it would unlock in propulsion, power generation, megastructural construction, and wormhole fabrication would be nearly limitless. Even as a theoretical concept, it inspires imagination and offers insights in the boundaries of our understanding of the universe. Neutronium. Neutronium is a term used to describe the ultra-dense material composed almost entirely of neutrons. This is what neutron stars are made of, and only the insane gravity of an object just below the threshold to be a black hole can hold this matter together at the unimaginable pressures and densities involved. It is akin to if you squeezed an entire mountain into something you could hold in your hand. Needless to say, this is not stable, requires forces beyond belief to squish together, and neutrons themselves decay in mere minutes. Yet it would be essentially incompressible by outward forces and invincibly strong against even nuclear-level attacks or monomolecular ultra-sharp blades. The reasoning goes that if you could stabilize it somehow, you would have indestructible armor, and it is popular in science fiction for this usage. But at a density of around 400 quadrillion kilograms per cubic meter, even a plate just a nanometer wide would mass 400 million tons per square meter, which might be a bit hard to carry around. In theory, you could build this down at the femtometer scale, and you might use it in femtotech constructions, in which case you might get all the way down to several hundred tons per square meter, which would be just one neutron thick. However, we could imagine that the same technology that let you hold it stably at such pressure might also let you nullify the mass of neutronium armor. We might imagine it then as something like Thor's hammer, which only he can move because without its cooperation, it's too heavy to budge. This would make sense as an object the size of that hammer would have a mass of around 1 trillion tons, more than Mount Everest. Parallel universes and alternate realities. As we explored in our episode on parallel universes and alternate realities, there are compelling reasons to consider the existence of realms beyond our observable universe. These aren't just alternate timelines, as often depicted in science fiction, but entirely separate dimensions or universes with different physical laws. The ability to access such places could unlock opportunities for mining resources or extracting energy from younger or uninhabitable universes. Inhabitable universes might provide even greater possibilities, offering paths to colonization that are far easier than traveling to nearby stars. Imagine stepping into a copy of Earth where proto-humans never discovered fire or went extinct, granting access to a pristine, habitable world as easily as traveling to a new continent. Civilizations could harness these alternate universes for energy, materials, and living space, potentially bypassing the need for galaxy-wide colonization. This scenario offers an intriguing solution to the Fermi Paradox, partially addressing the Dyson dilemma by suggesting that advanced civilizations might focus on exploiting alternate universes rather than spreading across the galaxy. However, such civilizations, with access to immense resources and no fear of interstellar neighbors, would likely still establish powerful telescopes and transmitters to communicate and observe their galaxy, even if colonizing it seemed unnecessary. This would make their presence detectable, offering other avenues to explore in our search for extraterrestrial intelligence. It is also possible civilizations with access to other realities might find some of them better suited for life than the one they came from, with fewer restrictions on energy or entropy or the speed of light, and indeed travel through congruent universes that were smaller or had higher speed limits is one of the more popular workarounds to achieving effective faster-than-light travel. Perpetual motion machine. A perpetual motion machine is a hypothetical device that can operate indefinitely without an external energy source. It would generate continuous motion or energy output without losing efficiency, seemingly defying the fundamental laws of physics. They tend to pop up a lot in science fiction and often by accident, as the author didn't realize that some technology or ability they introduced could be used to create one. Perpetual motion machines come in a lot of types, but we often classify them into 3 main types based on which physical law they appear to violate. The first type violates the first law of thermodynamics, that energy cannot be created or destroyed, just transformed. Machines of this type create more energy than they consume. As a sci-fi example, your classic portal or Stargate would seem to permit a perpetual motion machine by having one mouth of your portal be beneath the other one, so you could drop a rock into the bottom one and would emerge from the top one, gain speed falling, drop through the lower one, and appear again from the top to gain speed again. As we discussed in our Wormholes episode, such a scenario wouldn't work as described. The object would lose speed as it ascended, regardless of whether a wormhole was involved. In this case, it's important to note that the object gains speed by converting gravitational potential energy into kinetic energy, much like a spaceship performing a slingshot maneuver or utilizing the Yordanov effect to maximize its velocity. Many so-called perpetual motion machines that people have built or proposed appear to violate the first law of thermodynamics, but in reality, they often draw energy from an external source, even if it's not immediately obvious. These systems are not truly perpetual, they rely on hidden inputs to sustain their motion. Though to be fair, this can still be an awesome power source. Our second type of perpetual motion machine includes those that violate the second law of thermodynamics, that entropy increases in closed systems. These machines propose to extract all the usable energy from a system without any loss due to heat or friction. For example, a heat engine that converts all the heat energy into work without any waste. Realistically, in every energy transfer or transformation, some energy is lost as heat or disorder, making 100% efficiency unobtainable. And our third type are those proposed to remove all friction, drag, or resistance from a system. A wheel that doesn't slow down even though its axle should produce some friction, or the area it is in produces some drag. Even a ball spinning in the vacuum of space will be slowly halted by cosmic microwave background radiation, or virtual particles seething out of the false vacuum. Generally speaking, for these reasons, perpetual motion machines are essentially the ultimate Clarketech, as they are not outright forbidden. There just doesn't seem to be any pathway to them. That said, finding out that there was a greater reality we could draw power from, and infinitely, would not really be that surprising at this point, and would seem a more likely path to a perpetual motion machine, more or less a Type 1 than either Type 2 or 3. At the same time, machines seeking to minimize entropy from resistance are the goal of every engineer, and the notion is that you can approach a Type 2 or 3 machine, one that produces little entropy or has little friction or resistance, but you just can't make a true one that completely zeroes them out. Photogravitics and photoneutrino devices. One of the most fascinating effects, and one of Albert Einstein's lesser-known contributions to science, is the photoelectric effect. This phenomenon occurs when a material absorbs a photon of light and ejects an electron, producing an electric current. It serves as the foundation for photovoltaic materials that convert sunlight into electricity, as well as the reverse process, such as in LEDs, where electricity is used to emit light. The key idea is that the photoelectric effect allows us to convert photons into usable electrons, or conversely, electrons into photons. This principle demonstrates the broader concept of energy conversion, where different forces or forms of energy can be transformed into others, whether at a fundamental level or through mechanical systems like gears that redirect or translate forces. We might envision future technologies capable of absorbing sunlight and converting photons into gravitons or gravitational forces, potentially enabling artificial gravity. Similarly, a device that could absorb neutrinos and produce photons or gravitons would be revolutionary. Any material capable of significantly interacting with neutrinos would be remarkable, as the Sun generates vast quantities of neutrinos carrying substantial energy. Such a material could even facilitate advanced elemental alchemy. A hypothetical device that absorbs gravity and converts it into photons, neutrinos, or other particles could be incredibly useful. Imagine a platform hovering over a star, absorbing its gravitational and photon energy, holding itself stable while emitting harmless neutrinos. Such a platform could allow individuals to float or move about safely. In another application, a planet or star system could use neutrino beams to transfer power. These beams would pass through almost anything except specific receivers designed to capture them, enabling efficient and nearly lossless power transmission. Neutrino-based communication devices would also be groundbreaking, as neutrinos can pass directly through planets, allowing instantaneous communication without the need for wires or satellite relays. Although technologies to produce and absorb neutrinos or gravitons are far beyond our current capabilities, the fact that such particles exist makes these concepts theoretically plausible. If realized, they could revolutionize energy, communication, and transportation in ways that are currently unimaginable. Probability manipulation. If you could alter the odds of a coin landing heads or a dice roll, the potential applications would extend far beyond merely cheating at a casino. At the quantum scale, as best as we can tell, events are statistical rather than deterministic, meaning particle interactions are random and governed by probabilities. By altering the odds of when a particle decays or fuses, you could unlock groundbreaking possibilities, including advanced power production, novel weaponry, or even reversing entropy. This concept could also revolutionize space travel, as illustrated by the infinite improbability drive from Douglas Adams' classic The Hitchhiker's Guide to the Galaxy. This fictional drive didn't just enable improbable events, like objects teleporting a short distance, or transmuting, rocks turning into chocolate bars for instance, but also infinitely improbable ones, such as jumping instantaneously to the other side of the universe. Reactionless Drive. Normally, to move anywhere, you need to accelerate and gain speed, which requires pushing off something else. In space, where there's nothing to push against, we rely on carrying propellant to expel out the back, propelling us forward in accordance with the conservation of momentum. A reactionist drive, however, bypasses this need, either by circumventing the conservation of momentum altogether or by pushing against something present in space. In Star Wars, for example, the official explanation for why ships maneuver like atmospheric fighter planes is the use of etheric rudders. This references the historical concept of ether, once hypothesized as the medium through which electromagnetic waves propagated, before it was shown to be unnecessary by the advent of special relativity. However, as one of my professors used to say, proving the ether isn't needed doesn't mean it doesn't exist. there's always the possibility of some underlying medium, like the false vacuum, that could serve as something to push against or as a source of particles for propellant and fuel. Such a discovery would revolutionize propulsion systems, potentially enabling spacecraft to move without carrying onboard propellant, maybe by shoving off the ether, maybe by pulling particles out of it to use for propellant or fuel. This would probably circumvent the issue of violating momentum conservation, making a tantalizing idea for future exploration that might be in the realms of the plausible, though of course flat-out violating momentum conservation might be an option too, as we discussed in the mass manipulation entry. SFIA Intermission. We're headed into the final stretch, and it's a great chance to refill that drink or get another snack. But I want to thank you for joining us and helping make this show happen every week. There's a lot of work that goes into making episodes and running the channel, and it wouldn't be possible without around 1,000 folks who have steadily supported this show on Patreon, and I hope you'll consider supporting us in the future as we try to look at science and futurism, either on Patreon or one of our other methods like Subscribestar, PayPal, or even Snail Mail, and you can find out how by going to isaacarthur.net. And now, back to the impossible. Slow time fields. Slow time devices are a popular staple in science fiction and a subset of the broader topic of time manipulation, a concept we'll delve into later. However, slow time effects are explicitly possible under known physics. Gravity slows time, and relative velocity slows time, so it's not hard to imagine artificially producing such an effect. This opens the door to fascinating possibilities such as stasis fields. For instance, you could replace your refrigerator with a slow time box. To retrieve an item, you need to temporarily turn off the field, and instead of yelling at someone for leaving the door open and letting all the cold out, you tell them to stop letting all the time in. Other applications would be sticking a slow time bubble around someone injured to slow things until doctors could arrive. Fundamentally, the primary use for slow time devices would be buying time and preservation, such as keeping food fresh or preventing materials from degrading. However, in scenarios involving conflict or combat, you might want the opposite, a way to slow time for others or speed up for yourself. A slowed opponent would have less time to react, think, or act, giving you a significant advantage. On a broader scale, such technology could radically change how civilizations approach existence. For example, bored individuals might be tempted to skip forward in time, effectively leapfrogging through eras. This could lead to challenges in maintaining a stable civilization if too many people chose to hibernate for extended periods. We've previously discussed the concept of hibernating civilizations from various angles, and a technology like this would enable purposeful hibernation. It could allow societies to survive into distant eras, such as the late universe, when natural black holes have evaporated enough to become efficient power sources. This has the same problem with hibernation as usual, though. While you were sitting around in slow time, other people would and could be acting, gathering resources or preparing to attack you and take yours. Subverse Creation. When it comes to godlike and impossible feats, creating whole new universes is right up there at the top of it. And yet there are a lot of options for potentially creating new universes under this one, or to think we might be one of many universes underneath some greater reality. We use the term subverse to describe any type of universe that's spawned from and connected to another, and this could include creating a mini-universe in a bottle, or setting off new universes with each new black hole that is created from here, as some theories suggest, or even simply creating a simulated universe or virtual reality. Though in all these cases we would hold it was only a subverse if it were of a certain scope or complexity. A small pocket universe like is implied in some versions of Hammer Space might count, but a low-resolution simulation or a shared video game setting like a modern MMORPG probably should not. I would generally say though that the substrate does not matter. If you're building a whole new reality full of billions of human-level emulated minds on a computer, this is still a subverse. Such technology might be in our grasp even this century, and for that matter, if forming a black hole did create a new Big Bang somewhere, that might be in our grasp in centuries come too, not a nebulous superhuman future untold millennia down the road. Technological suppression zones. A popular trope in science fiction, especially in science fantasy, involves areas where technology ceases to function or certain types of technology are specifically disabled, like in Roger Zelazny's Amber series. Notable explorations of this concept include C.S. Friedman's Chord File series and Werner Vinge's Zones of Thought series, both of which creatively incorporate technological limitations as central elements of their world building. These works are not only inventive but also great reads. We can imagine places where basic physics or chemistry break down entirely, or where specific technologies are suppressed. Earlier, we discussed field nullifiers that could selectively disable certain systems. For example, anti-nuclear fields were a common Cold War-era science fiction concept designed to prevent nuclear weapons from detonating. In terms of realistic implementations, such scenarios could plausibly rely on AI and nanotechnology. For instance, a techno-primitivist society might inhabit a space habitat maintained by automated systems, while employing a network of scanners and nanobots programmed to detect and disable advanced technologies. Visitors might initially retain access to the devices, but over time, their technology would begin to fail unless adapted to the environment. With sufficiently advanced nanobots and a clever AI managing the system, this setup could precisely target which technologies to disable while allowing others to function. For instance, a friend or foe identification system might permit certain devices, like stunners or ray guns, carried by security personnel, to remain operational. Others might unban technology for certain circumstances, like a disaster or on some annual holiday for using advanced technology, or in certain places like schools for teaching their maintenance personnel. This blend of selective control and adaptability could create a highly immersive and intriguing environment in fiction or speculative scenarios, but it also isn't too hard to imagine this being used in real life, both for techno-primitivism examples and for weapon or 3D printer control in densely populated areas where folks might fear random citizens being able to print doomsday devices, or handguns able to fire mini-nukes out of them. Needless to say, a tyrannical government might use them for a lot of control too, but then they could also use all those scanners and nanobots to watch for bad behavior and brainwash people, as opposed to just shutting their technology off. Teleportation and gateways. In our episode on teleportation, we examined a few methods for getting from point A to point B instantly, but the main focus tends to be on sending a copy of someone's state, or the data file of their existence, to another location for copying. This is thankfully the sort of file that can be vastly compressed, since otherwise sending one person's atomic data to another star system might take billions of years. But there's no real reason to send a new copy of your DNA for every single cell in your body, let alone the exact atomic positions of every one of the billions of atoms in even your smallest cells. We can also potentially do this through quantum effects, but it's the same idea. You are not moving the atoms, you are copying yourself onto atoms already there. And by spooky action at a distance, it might be possible to teleport macroscopic objects over a long distance, like you or I to another planet, while at the moment quantum teleportation tends to be limited to a handful of atoms over very short distances. That said, there are a lot of ways you might move something besides cloning its data, and it might be that you take a bubble of space-time, which might include a person or object, and remove it from its current position and paste it somewhere else, or even when else. We have no good pathways to this, or more classic gateways, but we examined the option for stargates and their uses in our recent episode on stargates as an alternative to classic wormholes, and we also have no strict barriers, so this is Clarketech but also not strongly prohibited Clarketech. Tachyon Tech. Tachyons are hypothetical particles that move faster than light and also backward in time. They are thought to have imaginary mass as opposed to negative mass. They are not unique as particles that might have a backward motion in time. Some theorize that virtual particle pair production, where two particles pop into existence, then mutually annihilate a moment later, might actually be a particle moving forwards in time for a moment, then backward, basically looping into existence for a moment, then backward to erase itself, as an antiparticle acts very like a normal particle moving backward in time. Nor is time and particle type really unrelated. For instance, particles with real mass experience time. Particles with no mass experience no time, like the photon. If tachyons exist, they have some weird properties, like how they would gain speed if they lost energy, opposite normal things, which are more energetic the faster they move. It might have interesting properties as a potential shield too, as while regular matter resists being shoved on, but moves away in the direction of that force, and negative matter does the opposite, moving toward the force that pushed on it, the math indicates a tachyon would fly in a direction perpendicular to the force acting on it. And of course, the tachyon always moves faster than light and always moves backward in time, hence its usual interest for folks. For my part, I don't hold that causality can be broken, and thus would expect that if tachyons were real, they wouldn't permit time travel, thus why some of those other texts interest me. We have explored the actual science of tachyons and time travel in its own episode. Although the existence of tachyons doesn't imply you can move a person faster than light, any more than the existence of a photon permits something with actual mass to move at light speed. It takes infinite energy to accelerate anything with mass to light speed, and infinite energy to decelerate a tachyon down to light speed. That doesn't mean you can just flip them around to let you move someone FTL themselves. Thus, alternate technologies like something that when it got hit moves sideways tend to seem more plausible and interesting to me, and that includes some scenarios for power generation, hyperfast computing, and even options for instant but non-causality violating communication, and thermodynamics violating options. Time manipulation. Talking about tachyons inevitably leads to discussion about time itself, particularly how it behaves in non-uniform ways. It's important to note that time doesn't flow homogeneously everywhere. For example, time at your feet moves slightly slower than at your head because your feet are closer to Earth's center and thus deeper in the gravitational field, which slows time. This effect, known as gravitational time dilation, is caused by energy, not just mass. Mass is one form of energy, but other forms, such as heat and rotational energy, also contribute. For instance, black holes derive a significant portion of their energy from heat and rotation, in addition to mass. It's this total energy, not just mass, that warps space-time and slows time. Time runs fastest in the voids between galaxies, where gravitational influence is weakest, and slowest near the centers of massive objects. Notably at the Earth's core, where net gravity is effectively zero, time still runs slowest because the escape velocity, the speed needed to escape Earth's gravitational field, is highest at that point. As a rule of thumb, you can estimate gravitational time dilation by calculating the escape velocity and plugging into the standard special relativity equation as if the object were moving at that speed. This gives an approximate measure of how much time slows due to gravity. However, objects with significant time dilation effects, such as black holes, rotation and other factors often complicate the calculations, making this method only a basic guideline. As is often the case, if a phenomenon occurs naturally in the universe, we can imagine ways to replicate it artificially, potentially through different or more accessible means. One of our favorite megastructures on this show, which might get its own dedicated episode someday, if I can ever manage to secure some good animations or imagery, is a Birch planet. This is a multi-layered shellboard built around a massive black hole, potentially millions or even billions of solar masses in size. As such, it has very significant time dilation, and more so as you go to lower levels. Pushed to extremes, we might imagine layers where time flowed several times faster than in higher layers, as around truly giant black holes in the billions of solar masses, you can get event horizon radiuses in the hundreds or even thousands of AU. 1 AU or astronomical unit being Earth's distance from the Sun, and you might be building layers only a few AU out from that horizon, especially if you built a non-rotating black hole. And that's all viable under known science. We could imagine fields able to produce this effect more sharply and with less mass, or even ones that had time running not just slower than normal, but ultra fast, faster than the rate it moves in the cosmic voids, or even in reverse. Utility fog and smart matter. Utility fog is a futuristic concept involving a swarm of tiny robots called foglets that link together to form a flexible, adaptable network. Imagine these foglets as microscopic machines that can organize themselves in any configuration, creating physical objects, manipulating environments, or even forming virtual spaces around users in real time. Depending on the skill and sophistication, this might be something akin to microscopic Legos all the way down to femtotech micromachines that can configure into any atoms and molecules. This device could range in size from biological cells to truly subatomic particles, and the fog they form wouldn't need to be uniformly composed of identical droplets. Instead, they might vary in size and function, much like Lego blocks. While this technology could seemingly produce any material, it would come with limitations. For instance, the droplets could only bind together so quickly, and their bonding strength would inherently be weaker than atomic bonds. This means they wouldn't be suitable for creating strong protective armor or structural supports, except in bulk, or for a quickly deployed but weaker option, like giving a person a quick bridge across a river or shield from attack. They would also likely have heat limitations, struggling to operate in hot environments without breaking apart, and generating significant heat themselves during operation. A fog might be able to wrap you in a protective cocoon, but wouldn't compare to purpose-built shields or armor in terms of strength. Consequently, such technology would likely be used as a convenient multi-tool rather than the foundation of an entire civilization's infrastructure. For example, people might wear clothing made of utility fog, such as a versatile cape, but they wouldn't rely on it for all structural needs. Post-biological beings might even compose themselves entirely of this matter. Its effectiveness would depend on the underlying technology, but a realistic implication under known science would likely be slow to assemble and, while not excessively fragile, wouldn't be highly damage resistant. However, its ability to self-repair by plugging holes could allow it to absorb damage, and more advanced versions might repair or replace damaged droplets altogether. Key challenges would include power supply, sensor integration, and the strength of the mechanisms used for droplet-to-droplet connections. As discussed in our recent nanotechnology episode, a fog powered by wireless energy transmission, e.g. microwaves, would still require a rectenna no smaller than a quarter of the wavelength of the transmitted energy. In the microwave spectrum, which ends at the V-band, this translates to droplets needing to be at least a quarter of a millimeter in size for power or reception. This is roughly the smallest size that the human eye could perceive as individual specks at arm's length. Smaller droplets are theoretically possible but would require different power sources. Without Clarketech innovations, this likely limits them to chemical fuels such as sugars used in biological systems, which would impose similar energy and efficiency constraints to those seen in nature. Even with these limitations, utility fog would be extraordinarily versatile, allowing users to quickly assemble rough forms of almost any object. However, tools created this way, like knives, pry bars, or hammers, would generally be far weaker than those made of simple steel, even if the droplets themselves were made of hyper-strong materials like graphene. This makes utility fog a valuable tool for many purposes, but not a complete replacement for traditional materials in all applications. We explored many of them, along with some practical limitations and interesting applications, in our episode on smart and programmable matter. Wormholes. Wormholes are hypothetical structures in spacetime that act as shortcuts, connecting two distant points in the universe through a tunnel. While these include other options, which we explored in our episode on stargates, the best known and most discussed comes from the solutions to Einstein's equations of general relativity. These wormholes, also known as Einstein-Rosen bridges, would allow for rapid travel between vast distances without traversing the intervening space. However, for a wormhole to remain stable and traversable, it would require exotic matter, with negative energy density to counteract the natural tendency of the wormhole to collapse. This exotic matter is speculative and has yet to be observed, and as we discussed in our negative matter section, is problematic in its predicted behavior, probably violating conservation of energy and momentum. While wormholes are a staple of science fiction for enabling fast light travel or interdimensional exploration, their feasibility remains uncertain. They also tend to require huge amounts of matter to make them work, including tons of negative matter, and can be used to violate causality in the case of wormholes with both sides in the same universe permitting time travel. Wormholes to other universes pose fewer challenges and may be more plausible and more beneficial, as they could let you colonize other universes or connect a young and highly energetic universe to a power plant or spaceship drive to allow a free energy source, or at least one that is external to our own universe. See our Wormholes episode for more discussion of them. Zero-point energy. Zero-point energy and vacuum energy, as discussed in our episode on the topic, explore the idea that beneath our observable reality lies a teeming supply of particles and energy. Imagine our reality as the surface of a deep ocean, with energy and particles constantly bubbling up from the quantum foam beneath. This is why we refer to the concept of a false vacuum, as even the emptiest regions of our universe are not truly voids, but filled with particles momentarily popping in and out of existence. Zero-point energy is a compelling form of Clarketech because, while we cannot be certain how much energy is available or how to harness it, theoretical approaches suggest immense potential. Tapping into this energy would likely not provide infinite power, but could unlock a supply orders of magnitude greater than anything in our observable universe, available anywhere, even the most remote and empty cosmic voids. It may also allow access to other realities with different false vacuum levels, or at different ocean depths, so to speak. Such a resource would have profound implications. Civilizations capable of exploiting zero-point energy might distribute themselves widely across the universe, much like homes and properties relying on well water must spread out to gather sufficient rain to refill their wells. This could influence the Fermi Paradox, shaping how advanced civilizations distribute themselves and how we might do so in our own future. The ability to tap such a universal energy source could fundamentally redefine interstellar expansion and survival, offering insights into the behavior of advanced societies, assuming, of course, this technology is feasible and not simply theoretical magic. So there we are, Clarketech. Some may never be more than sci-fi dreams, others might surprise us and arrive just over the horizon. Time will tell. But I did want to thank you for taking the time to join us today. And if it's been a fun hour and a half, I recommend you our other feature-length compendium episodes. Whether these technologies are impossible or not, this show could only be possible with all of you watching, and I want to take a moment to thank everyone for all their support every week. I hope you'll consider supporting the show by joining or supporting us on Patreon, and joining us next week for our episode Black Sun Rising, living on a planet around a black hole. And in the meantime, thanks for watching, and have a great week.